And we are live.
Welcome, everyone. Welcome to our meetup today with Jane Adams. For us who don't know us or don't know me, I'm Marilia. I'm part of Data Visualization Lisboa. We are a group of data viz professionals who have this idea to make data accessible, as accessible as possible. To do that, we have been doing monthly meetups. You can find them all in our on our YouTube channel. And now we have a newsletter called Pastel de Data, pun intended, that we launched our first edition last month, and we will briefly launch the second edition. You can learn more about it in the end of this meetup. And we also have been doing reviews of DataViz articles on our LinkedIn channel. So plenty of opportunities to know us more and know us better. But now I'll give the floor to Sarah and Jane.
Okay, so it's my pleasure actually to introduce Jane Adams. So Jane is a data visualization researcher and practicing emergent media artist. She's currently pursuing a PhD in computer science at Northwestern University. And in her last position as a data visualization artist in residence at the University of Vermont Complex Systems Center, Jane developed exploratory visual analysis tools for population health, genomics, and social media. Her data visualization work has been featured in Wired, and her immersive art installations have been exhibited in galleries as well as the Forest of Vermont. So today she will tell us all about exploratory analysis of high-dimensional data. And so thank you so much, Jane, for accepting our invitation and for you to be here today with us. So please, the floor is yours.
Wonderful.
See you in a bit.
Thank you so much for that warm introduction. It's an honor to be able to share some of my story and some of my research. So I wanted to start off, before I get into the nitty-gritty details of exploratory data analysis, I wanted to share a little bit about kind of my history from graphic design to computer science, because it's been quite the adventure over the last 5 years. So in 2015, I graduated with a Bachelor's of Fine Arts in Graphic Design and Digital Media from Champlain College. The majority of my work was in print design and layout, but I did do a small amount of front-end web development. And then I began working at Dealer.com as a media design intern. So Dealer.com creates digital display advertisements for 17,000 car dealerships all across the United States programmatically. So they actually interface with the database of car inventory and then pull those images of cars and the pricing and things like that into these digital display advertisements, which use the Google real-time bidding system for ad placement. And so that kind of helped me get a little bit more coding under my belt, but I was sort of feeling like I wanted to do something a little bit more meaningful in terms of like domain application for coding. And so I ended up going back to school for a Master's of Fine Arts in Emergent Media. Which was a very interesting kind of nebulously defined program that was sort of split into two different approaches. So the first approach was thinking about emergent media historically and how human systems respond to new technology. And then kind of the other side of that was looking at emergent technology that was kind of at the forefront of the landscape today. So everything from physical computing, experimenting with Arduinos and Raspberry Pi, to mobile visualization, interactive media, and immersive data visualization art installations. So this was kind of a really eye-opening program for me because it put me directly in contact with some of the most like cutting-edge technology, but in the context of fine art and expressive design. And so I really got to kind of think through some philosophical questions that I was having about what I wanted to do with my life and what interested me, while also getting some firsthand experience kind of hacking together on different new technologies. So my Master's of Fine Art thesis was called Universalities of Inquiry, and it was about just thinking through the idea of the similarities between science and art, because throughout my adolescence, I had often sort of thought of science and art as oppositional to one another. But then through this emergent media program, I was finding that there were actually a lot of commonalities between the scientific method and the sort of design thinking process, in that they were iterative, they were necessarily communal. They required, interfacing with existing ideas and building off of existing research, and so that was kind of the basis of my MFA thesis, was universalities of inquiry. So even though the scientific inquiry is ideally attempting to be possibly asymptotically so objective, and design and art is often very subjective, they're kind of two sides of the same coin in terms of inquiry. And so this was some pictures from the installation that I did for my MFA thesis, where I kind of looked at three vectors of inquiry, one being explanation, like scientific communication, or how do we, once we have some idea or some experience that we live through, how do we communicate that to the outside world, and what encoding methods do we have for that communication? What things do we see kind of like as motifs that come up throughout history repeatedly as methods of explanation across science and art? The kind of second vector would be iteration. So, the idea of failing early and failing often, the idea of revising a hypothesis when our observations perhaps don't support our initial hypothesis. And basically just moving through things in a prototypal mindset, and trying things over and over again. And this design thinking process I've actually been applying more recently to my scientific research, and it's incredibly useful, as opposed to maybe a traditional waterfall method where you are starting from point A and ideally moving linearly to point B, because when you have this iterative approach where you're making small steps and then revisiting your kind of original idea and adjusting course accordingly, you don't run the risk as much of having to lose resources or lose time, because you kind of have that tolerance to failure built into the system. And so you'll actually see in this installation here that I have some frogs and fish and aquaponics stuff as sort of a symbolic representation of that iterative kind of homeostatic mechanism. So we can look to nature to see how a lot of systems in nature also kind of start small and grow iteratively, and that really kind of is fundamentally the basis of our idea of survival of the fittest, and adaptability is our ability to kind of respond to failure and recover from failure, and in fact build our processes for development around planning on failure. And then that third vector of inquiry is participation, and the idea of network publics, and the idea of building our research and our artworks based on the research and artwork that has come before it, and also the kind of concept of distributed systems and participatory design as well. So all of those ideas kind of were circulating in my conception of what it means to develop an inquiring process, and how design and science kind of both are fundamentally those processes of inquiry that have explanation, iteration, and participation baked in different ways. I'm also a practicing artist, and so in addition to my kind of day job research, I really like kind of experimenting and building just like fun, immersive artworks. And so some of these that you see here are from my work with the Illumination Collective. So we, when I lived in Vermont, I joined and cultivated this artist collective where we did site-specific installations. So this first picture on the far left is an installation I did with color-changing light bulbs with lamps that were reactive to motion. And so you might walk through a forest and have all of these tiny lamps kind of light up as you walk through. On the bottom here, we see another artist in the collective did an installation of glowing whales at our local aquarium for a New Year's Eve event. And then on the right here is an image. You'll see some curtains tied to trees and some furniture. I actually transported my entire living room into the forest, kind of wanting to imagine, what it would look like if my living room existed in the forest. And there's actually some projection mapping here of a fireplace. So there was actually kind of a crackling fire simulated using projection mapping. And so maintaining an art practice is really important, I think, for my mental health and for my personal development, to have those spaces that aren't so rigidly constrained by scientific process and the publisher perish kind of mindset of academia. This also is another sculptural work that I did, which is an aquaponic diorama. So it's basically a dollhouse on the top and a fish tank on the bottom. And the fish tank is a, once again, self-sustaining homeostatic mechanism where the water from the fish tank, it becomes fertilizer for the plants. And so the water is automatically pumped up into the plants at the top and then filtered back down through and recycled back into the fish tank. And so this was, an extension of my thoughts on self-sustaining ecosystems and imagining urban farming infrastructure and what that might look like if it was kind of built into our systems in the same way that we have an electrical grid and a plumbing grid, that we might have an aquaponics urban farming grid as well. And then more recently, during the pandemic, I kind of had to pivot away from what I was most comfortable with in terms of interactive, immersive artworks and large-scale sculptural works. The makerspace in my town shut down, and we no longer had gallery shows happening anymore. And so I ended up pivoting into using generative adversarial networks as an art medium. So generative adversarial networks are abbreviated as GANs. And they're functionally just two neural networks, a generator and a discriminator, that are working together to create realistic images or text. So the discriminator has seen a whole bunch of real samples, say of images. The generator has not. And the generator is just working to keep trying to fool the discriminator into thinking that it's created a realistic looking image. And the discriminator learns when it's been fooled, and so it becomes a better judge over time. And the generator also learns when it has succeeded in fooling the discriminator, so it becomes a better faker over time. And so the two neural networks kind of converse with one another on a supercomputer for a very long time. And at a certain point, we get to a point where the images are somewhat indistinguishable from the original real samples. And so this was like one of my first passes on using GANs as an art medium, trained off of Hayao Miyazaki's films. So some of you may be familiar with some of those. For example, Spirited Away, My Neighbor Totoro, Princess Mononoke. And so this was kind of my first pass, but one of my favorite things about Hayao Miyazaki's designs is actually his landscapes. And so I started thinking about kind of what I knew about machine learning and about classification of images, and applied k-means pixel clustering to all of the video frames to find the top 5 most dominant colors for each one. And then the idea was to filter by the hue saturation value range to only collect bright blue and green images, which hopefully would be landscapes. And so on the left here, you can see some stills that were excluded from the second model. So you can see the average color, but then also the 5 dominant colors that were identified by k-means pixel clustering. And so the warm palette images were excluded from the training data, and the cool palette images on the right were included in the training data. So it contained mostly landscapes, ocean, and sky with some small figures. And so on the left here, you can see the original network outputs from all of the Studio Ghibli images. And then on the right, specifically just the landscape. So those were the ones, the model that was trained only on images that were selected as a subset using k-means pixel clustering for blues and greens. You can still see that some certain characters make abstracted appearances. For example, Kiki from Kiki's Delivery Service, Totoro, Princess Mononoke, etc. So I've been training a bunch of these models. This is another one that I really enjoyed developing, and I actually used a lot of my graphic design background in order to curate training data. So I wanted to create a model trained on plants, but I was having trouble getting the volume of training data that I really wanted, because to accurately train one of these models, you really want several thousand images for training data. And so what I had was a bunch of unpotted plants and then some empty pots. And in the middle here, you see my plant pot adjacency matrices. So these were these grids that I created in Adobe Illustrator, and I set to task listening to some podcasts and music, and just manually potting some of these digital plants into some empty pots in order to artificially increase the training data size. And so in the top right, you see this GIF. These are all manually generated training images. And then in the bottom right, the exported latent walk from the StyleGAN 2 model. So latent walk is just kind of a fancy way of saying that this is a tour through the brain of the generator network functionally. And it's what we're looking at here is a linear interpolation between probability distributions across all of the different dimensions of the neural network. But that's maybe kind of a complex explanation for something that I think basically is just really beautiful and delightful to look at, and kind of fun to share, and gets people interested in neural networks when maybe they might not have otherwise been as curious. So I've been making a lot of AI art using these models that I've trained myself. So if you want to follow at Nodradec on Twitter or Instagram for more AI art, I also share a lot of work of other AI artists, and I moderate a Discord channel for GAN artists as well. But that's kind of just a side note about some of my personal artwork, but I'm here today to talk specifically about data visualization and exploratory data analysis. So in 2018, after I finished my master's degree, I joined the University of Vermont Complex Systems Center as a data visualization artist in residence. This was a position that didn't exist before I joined, and so it was kind of up to me and the rest of the team to decide what that really looked like. But one thing that I really loved about the Complex Systems Center is that it kind of looks at these multivariate, temporally dynamic systems in which we see emergent behavior. So my boss, Peter Dodds, has a great explanation for why we need systems thinking. He says you can't see a hurricane in a droplet of water, and you can't see a financial collapse in a single dollar bill. So if we're only studying water droplets, or if we're only studying dollar bills, then we're not really fully understanding or being able to predict the hurricane or the financial collapse. And so it's only through studying these things as complex systems that we get a sense of kind of what that emergent behavior is. And then in the top right here, you'll see this blue, orange, and red network here, emblematic of the classic SIR model of susceptible, infected, recovered, which epidemiologists have been using for a long time to think about contagion. and became especially relevant over the last 2 years as the pandemic kind of swept the world. And so in my capacity there, I was doing some work with Twitter data and computational social science, but we also had a research partnership with MassMutual Life Insurance. And so in that capacity, I was interested in exploratory data visualization for high-dimensional data. And I'll touch more on that in just a moment. But after that, since this spring, since this fall, I've joined Northeastern University now as a PhD student in computer science in data visualization. And my kind of first research project in that capacity is creating interactive exploratory visualizations of the vasculature of the brain, in the hopes that we can develop better planar embeddings of network graphs of cerebrovascular systems in order to identify neurological anomalies in clinical settings. So, for example, different types of stroke, aneurysm, stenosis, other potential neurological anomalies. And so here on the left, you can see kind of my early steps in abstracting the vasculature into a more simplistic kind of cubist node link diagram. And then on the right, taking the complex network and flattening it into a force-directed layout weighted by the length of the arterial structures. So for visualization of high-dimensional data, I'm sure that I'm sort of preaching to the choir here on why we need visualization, but these two GIFs are some of my favorites for explaining the value of visualization. So on the left, we have Simpson's paradox, in which we might see that the fit line, the correlation among data points, when conditioned on some categorical value, may be completely different than the kind of overall correlation across data points. And so another great reason of why it's important to facet our data and to look at different angles and really try and utilize all the information that we have about different groups or subsets of our data points. And then on the right, the data source dozen, inspired by Anscombe's quartet. Basically, these are 12 different charts of X and Y coordinates that have the same summary statistics, mean, standard deviation, and correlation. But very quickly, when we visualize them, we can see how different they are. So when it comes to high-dimensional data analysis, Pairplots can only take us so far. So this is a really common visualization that we see when looking at something like the IRIS data set, which is kind of a great toy data set for like intro to data science classes, where we're trying to understand the relationships between a couple variables in a data set. But the problem is that with Pairplots, here we're only looking at 4 variables. And so then across the identity of this matrix, we see the histograms of those variables, and then all of the scatter plots just comparing, variable 1 to variable 2. Across these quantitative values. But when we get into really high dimensional spaces, it can be very challenging to imagine looking at, a 10 by 10 grid of these charts, even, never mind 100 by 100 or 1000 by 1000. And so we really have to come up with some new ideas of how we can visualize some of that data and still interact with the raw underlying information. So in my research capacity at MassMutual Life Insurance, and this is a really common application across a number of domains, we've got a bunch of data from lots of people, for example, and we've got information, say, about their demographics, about their medical history, about their policy choices, things like that. So we have some M by N matrix of observations and features with some number of responses. And for example, maybe we could compute similarities between many individuals for one feature. and build a similarity network for a single feature in which, say, we are evaluating some concentration of a chemical in people's urinalysis or something like that. And then we want to cluster individuals by the occurrence of that chemical. But one thing that becomes kind of challenging there is then maybe we have some network that's weighted only by this one variable, but if we're trying to look at, a couple hundred variables, we end up with a whole bunch of networks of individuals. So instead, we kind of move along the other dimension. So instead of creating a similarity network of individuals, we consider all responses to each pair of features. And we build a single matrix of features for all observations. So here, contrasted with the previous network, the nodes correspond to features, not to people, and the information for all people is included in each edge. So if we're comparing someone's incidence of heart disease versus their taking of cholesterol-lowering drugs, we would compute some similarity score across all of the individuals for those two dimensions. And here I'm using dimensions, variables, and features kind of interchangeably. It kind of depends on your domain application, which is the most common use case. But the word features kind of comes from feature engineering and the world of machine learning, which is kind of where this visualization is headed. And so how do we compute that similarity, or how do we compute that weighting of the edges among each of the features? Well, there are a couple different examples from existing literature. So one is the association network. This is also often applied in market basket analysis. So in this example, we have some binary value. In market basket analysis, it would be whether or not some individual bought an item. In this example that I'm showing here, this is some animal name and then whether it has some different characteristics. So, hair, feathers, does it lay eggs? Does it make milk? Is it airborne, etc.? And so from that structure, we can compute the lift, which is based on the conditional probability. So given that I know feature X, how much better is my prediction of feature Y? And so we see here that the color scale goes from 0 to a little bit above 3. And so if we look to, for example, one of the darkest spots on here, airborne versus feathers, we can see that if an animal has feathers, it's 3 times more likely to be airborne, is basically what that lift measure means. So it's X times more likely is what lift encodes. And then on the right, we can imagine that if we took that association network and then put edges between the features dependent on the lift between the two, then we would end up with this network graph that kind of tells us a little bit about the similarities between certain features. Similarly, correlation networks function much the same way, except in the last example, you recall that we had binary values, but here we have quantitative values. And so rather than it just being yes or no, it's some quantitative value. And once again, we have animals and then their characteristics. So their color, their fur pattern, whether they have tough skin, if they have flippers, if they're big or small, etc. And so correlation networks function much in the same way, except that you'll see here that there's a diverging palette because while lift will go from 0 to some number of times more likely, correlation will have either perfect positive correlation, perfect negative correlation, or somewhere in the middle. And so here, this is showing the correlation matrix with a support threshold. So In our use case for MassMutual, we also had instances where it was very rare that someone had answered both questions. And so we wanted to also filter based on support. So we wanted to say, okay, I want to know if two variables are really well correlated, but only if we have a sample size of at least 75% of our respondents, for example, so that we're not kind of relying on some spurious correlation that is only the result of having, two answers, two people who had answered both questions. So correlation networks are also really common in genomics analysis. So WGCNA is weighted gene correlation network analysis. And here you're looking at the co-expression or gene dependence maps based on research using like CRISPR technology in order to create similarly these network diagrams and cluster dendrograms of the relationships between genes. And so I had done a little bit of research on this with some colleagues when I did a research retreat at the Complex Networks Winter Workshop, where instead of building out correlation networks of genes, we actually were building out correlation networks of cell lines, and then trying to understand the homophily or heterogeneity of cancer type. So our question was basically, if we generate a network graph of cell lines from a bunch of different types of cancer, whether it be lymphoma or lung cancer, breast cancer, are we going to see that cell lines from the same cancer type are clustered together based on their gene dependence, or are we going to see that there's more heterogeneity? And the reason that we wanted to do this was because oftentimes there are existing gene therapeutics for that are FDA approved for one kind of cancer. And if it's possible that those therapeutics could also target genes in order to treat a different type of cancer, then the time to regulatory approval is much shorter for existing therapeutics that have already been through the regulatory process once. And so these were some of our network visualizations that we created based on different cancer types. And then this is just a scatter plot showing the number of cell lines versus their homophily score. And so we can see that further up, we have kidney cancer and leukemia. So their genetic dependence rankings are more like cell lines of the same cancer type. So kidney cancer from one cell line is more similar to kidney cancer from another cell line, and same with leukemia. But down at the bottom, we see lower homophily, which indicates that the genetic dependence is more like cell lines of different cancer types. So there might be more heterogeneity in brain cancer or skin cancer, sarcoma, or lung cancer. And so those could potentially be interesting avenues for looking at therapeutics that could be used for cross-treatment. So moving back to the conversation about the MassMutual data and thinking about life insurance, we have a lot of different data types, cardinal, quantitative, binary, and categorical. And as I had mentioned before, association networks are great when you have binary values. Correlation networks are great when you have quantitative values, but that cardinality and those categoricals, we wanted to be able to create some sort of feature visualization, feature network that would allow us to make comparisons across different, mixed data types. And we also have a lot of missing data, so we want to be able to filter those out. Additionally, some of our quantitative values are normally distributed and some of them not at all. So it's really important that we allow the researchers, actuaries, to be able to actually look at the underlying distributions. Similarly, some of our binary values are evenly split, some are not, and some are actually unary. And so even though we would think that it would be like a yes/no question. The fact that you're asked this question may be indicative of the fact of some underlying information in the first place. And so maybe all of the answers are yes, because people who we would expect to have a no answer were not asked the question in the first place. And so for this project, which we're calling Sirius, we created network visualizations that were weighted by mutual information, so a measure of how much we learn about one feature from another. And so you could imagine here that this is, looking at someone's heart rate and then their taking of some sort of statin drug, for example, and we'll see these marginal distributions vary significantly across that binary value of whether or not someone is taking a certain drug. And so edges are drawn at a mutual information threshold value, and clusters are assigned based on a clustering algorithm. So nodes correspond to features, and edges are unweighted and represent pairs of features. So if a feature pair has high mutual information, we draw an edge between them, and feature pairs with low mutual information are not connected. And so here we can see just kind of anecdotally like what those individual plots would look like for one feature versus another when we're comparing discrete versus discrete versus continuous, or continuous versus continuous. And so the top row, high mutual information. So given that I know variable X, my prediction of variable Y is significantly improved. Whereas on the bottom row, low mutual information. So given that I know one feature about you, it doesn't really improve my knowledge of another feature. And so feature pairs that would generate charts like the ones on the top row would be connected in the network graph, whereas ones that would generate charts like those featured in the bottom row would not be connected in the network graph. So the feature network suggests specific feature pairs to visualize based on which pairs provide maximal information for hypothesis generation. And then different visualizations are used for different types of data. There's also some like sparsification that happens in the network graph in order to sort of be locally contextually aware of the relationships among features. But I'll kind of leave that after the Q&A session if we want to get into more about sparsification. And yeah, this is that backbone sparsification method kind of illustrated. But once again, I'll get into that if we're curious about it. And so here we see a feature network of some characteristics of individuals in a data set. This is an ICU mortality data set, so it's anonymized information, but it is from an emergency room, just thinking about kind of what features are related to one another in a large population of individuals. And so we see bilirubin, which is something created by the liver, and then liver cirrhosis and sort of the conditional distributions of bilirubin based on someone's cirrhosis diagnostic status. Similarly, we see arterial dissolved CO2 versus tumor presence in individuals. And this is kind of the latest pass on Sirius that is still in development. But the idea here is you can hover over edges and it will show you the pairwise comparison of two variables. And so you see here that there are box plots when it's a discrete versus continuous variable, kernel density scatter plots when it's a continuous versus continuous, and heat maps when we're looking at discrete versus discrete. And all of these charts are interactive. So as we mentioned before, the Anscom's quartet and the data source dozen, still really important to be able to look at the individual underlying data points while also exploring this kind of bird's eye view of the feature network. So this is just kind of one way of thinking about high-dimensional data representation. I've also shared the slides in the chat, and hopefully we can repost those into the general chat as well, because there are a lot of other existing resources that are super great for similar kinds of exploration. So this is the Hierarchical Clustering Explorer, which is a rank by feature framework based on correlation coefficient. And so you can see these dendrograms are sorting the features by their similarity. And then once again, being able to, in the bottom right there, look at the individual scatter plots for all of these quantitative values. Dimension projection, so similar idea, except that instead of networks, these are projected into a two-dimensional space using a different kind of weighting mechanism. Network visualization, so generating networks based on the conditional distributions of underlying values for multivariate relations. And all of these kinds of dimension projection tools are kind of precursors, I would imagine, for machine learning applications to dimensionality reduction or feature engineering. So where we might want to extract principal components or cluster our dimensions in order to move from extremely high dimensional spaces to low dimensional spaces. Feature selection. So contrary to our intuition that we want to throw as much data at a problem as possible, actually we know in practice that sometimes reducing the number of features that we put into a predictive model can actually improve our prediction. So finding out kind of which features are optimal or have the highest importance for a predictive analytics task can actually improve our outcomes significantly. And so all of this kind of requires thinking about high dimensional spaces and then moving from higher dimensional spaces into lower dimensional spaces. And if you've ever done any research on map projections, you know that there are 1,000,001 ways to project a globe onto a map. Similarly, there are many, many ways to project high dimensional spaces into a lower dimensional spaces. And so these tools, which are not dimensionality reduction tools, but are just dimensionality exploration tools, kind of allow us to make more informed choices about which dimensions we're combining into one or removing from our analytics. And then also manifold learning, similar approach, basically taking something in high dimensional space, flattening it out into two-dimensional space. And we can see here all of these are different manifold learning approaches to the same task with very different results. So I know that was a lot, so I'm really excited to hear what kinds of questions you all have, but thank you so much for listening. Feel free to follow me on Twitter. My website is here also, and I'm just Jane Adams on LinkedIn.
Thank you very much for this talk, Jane. It was very interesting. As you said, a lot of information. We have a couple of questions. Maybe we can start with a more generic one. So you have you started as a graphic designer. Now you are a researcher. You are also an artist, and you have been doing interesting projects in all of these areas. We have maybe some people in the beginning of the career also had this lot of interests, different interests, but in some ways they align, but they don't know exactly how to position themselves or how to better tell people what they do or they want to do. Do you have any tips or advice, or do you want to share a bit more on how you positioned yourself at the beginning of your career?
Yeah, that's a great question. I guess visualization is a very large space to exist in. And so I found very quickly when I first was starting out and sort of trying on the hat of data viz person, that if you talk to other data viz people, they will ask you a lot of extremely specific questions about, like, well, what do you mean? Are you info viz? Are you sci viz? Are you sci com? Are you explanatory, exploratory? Are you a data journalist? Are you, and so I think, yeah, there's a very vast landscape in which to position oneself. And for me, I think it was helpful, first of all, to think about what I didn't want to do. So as important as it is to know what you want to do, it's also important to know what you don't want to do. And so I knew from kind of my experience in like the corporate world and in marketing that like dashboards and marketing wasn't really the direction that I wanted to go in. And I was deeply, deeply curious about like complex science, like neurology and genomics and ecosystems. And I basically, I think visualization is wonderful because it gives us the ability to learn about lots of different things and kind of try on different hats. And so while, I don't really picture that I would ever be the kind of person that would, study brain science for 4 years at university, through visualization, I can say, that's maybe something that I'm interested in, and kind of try on that hat for one project and work with domain experts. And then, have the flexibility to say, I'd like to continue doing this, or maybe this doesn't really spark joy for me, as my mom, who loves the KonMari method, would say. So I would just say maybe try on a bunch of different things and see what makes you happy or what you hate. Also, is an important data point.
Super, thanks. So before going to the more technical questions, because we have some already in the chat, but following your comment now, I wanted to know more about the experience that you had in entering a complex system group like Center. With such a different background, I imagine how your team perceived you. How did they understand exactly what could you add to the team? How the projects were run. So how was it basically coming from design, entering a complex system center, and not having, hopefully, this like lost in translation?
It was certainly challenging, but I'm also like incredibly grateful, first of all, to my supervisors who gave me a lot of research autonomy, while also not sort of abandoning me, right? That's like a difficult duality to hold, to be, there to rely on and to answer questions and to be available for feedback, while also kind of leaving some room for exploration and for, as I mentioned before, iterative development and also failure. And that definitely was one of the critical parts of my work in complex systems, and joining the College of Engineering and Mathematical Sciences as someone with an MFA was taking that design thinking approach and saying, okay, rather than spending 6 weeks building an entire React app using D3 to create some visualization that may or may not actually answer the question that we're trying to answer, is just not an efficient use of resources. And so I had to I dove a lot deeper into Python, and Python is still kind of like where I'm most comfortable now, because the time from idea to visualization generation is so much shorter, at least for me, and maybe it's different for people that have been working with JavaScript for a really long time. But for me, I just felt like using kind of out-of-the-box packages like Plotly, like Seaborn, like Matplotlib, allowed me to have kind of this layer of abstraction over the visualization, so that I wasn't saying, okay, I'm going to draw an axis, and then I'm going to add tick marks to the axis, and then I'm going to draw my data points, and I'm going to, enter and exit. All of that kind of minutia, I think, is really powerful once you're getting into like the final visualization step. But for prototyping, like I try to make 50 charts an hour in sort of the iterative design step before I get to a place where I want to start building something that's more resilient.
And I guess the Python helps as well to, like, your colleagues probably would work in Python as well, no? So it's maybe easier to have a common ground at least of understanding.
Mm-hmm.
Okay, super, thank you. So
now we are going to a bit more technical questions from our audience. When you were talking about the networks, we had this question. So, is it possible to include causation in these networks? And a follow-up, or to estimate causation, not only correlation?
Yeah, that's interesting. I've done limited research on causation, mostly because the tools that I'm developing are for exploratory analysis rather than explanatory. And that's an important distinction that I make in kind of defining my niche as a visualization practitioner. But I would say that it's possible. I know through in complex systems research, sometimes you can do cohort analysis in order to possibly think through some ideas about causation. But generally, it's funny actually that I'm working in this area of feature exploration and thinking about machine learning, because I'm actually frankly terrified by machine learning in its potential to misconstrue reality a little bit. And so these exploratory visualizations are my sort of antidote to the black box model, because I'm sort of still forcing people to look at the individual data points that make up those summary statistics that we see. And also one of my motivations for developing and iterating on these tools is the idea of identifying proxy variables. So that was one thing that Mass Mutual was concerned about, as well as the current regulatory framework for avoiding discrimination in predictive models is to say, if we don't include race, we couldn't possibly be discriminating on race. And if we don't include gender as a variable, then we couldn't possibly be discriminating on gender as a variable. But we know as data scientists and as data viz practitioners that just because a variable isn't included in a model doesn't mean that you don't have these proxy variables that could potentially result in bias. And so that's kind of one of my thoughts is with these exploratory analysis tools, that it might actually help us to better identify those proxy variables and to think about the ways in which just throwing random variables into a predictive model might not fully get at the underlying reason for why the distribution looks the way that it does.
Yeah. Okay, perfect. So we move to the next one. So how can we avoid the dreaded hairball when the number of nodes in a network exceeds 100, 1000?
Mm-hmm. Yeah, that's a great question. And so I mentioned that I'd kind of skipped over the backbone sparsification step there in my presentation. But the basic premise there is that, and there are a number of different sparsification methods for networks, but the idea there is that you can basically compute an alpha significance value. So how sort of statistically anomalous is this edge for that particular node, and then dynamically cut the hierarchy according to that alpha significance threshold. And so what that does is it decreases the density of your densest hairballs in the network, while also kind of preserving the outside edges. of the network. And so I actually, let me see if I can share. So this is, I apologize for the not great visualization here. It's still kind of clunky, but this is a new version of Sirius where previously I was computing the alpha value and just kind of picking the optimum based on the maximal number of connected components. But now I'm actually implementing it so that the users can have more control over this. So the idea here is as you adjust the alpha value, you see this blue line here. So this is the number of edges. So the network goes from very sparse to extremely dense. And the number of connected components actually goes from 15 to 16 and then back down. And then in red here, we see the ratio of the first component to the second component. And so what we want is some relatively low ratio of the first component to the second component, which would mean that they're kind of similarly sized. And we also want a high number of individual connected components so that we don't have an extremely dense network. And so we can see as we adjust this alpha threshold up, we're getting more and more connected nodes. And then here, this is also allowing us to adjust the mutual information. And so if we have, a low threshold of mutual information, you see that hairball does start to develop. And so using these different sliders, we can kind of dynamically sparsify the network and iteratively explore.
We have another question also related to this. Why use a filter in the visualization about correlated features if the correlation is not strong?
I'm not sure I fully understand that question. I guess if the question is, so the idea with correlation networks is that you would only draw an edge between features that are well correlated. So
I'm not sure if João wants to follow up on the question, if he's still here. Let's wait.
Yeah, let's wait some minutes. I have
Yes.
maybe a question, not so technical, but I was wondering about the applications of this Sirius. So you mentioned so market basket analysis and hospitalization, or at least some healthcare related data analysis. But I'm wondering if we can, what other applications you have been exposed to or by, because people used it for different purposes, and can you share some?
Yeah, that's a great question. So I've used it for, as we mentioned, genomics, market basket analysis, healthcare information. The demo that I was just showing was actually information about home prices. So there's a bunch of information about, the size of someone's garage, or what neighborhood they live in, or what the last purchase price was. And so if you're, trying to understand clusters of features for, say, for example, some predictive analytics challenge on Kaggle or something like that, this could be an interesting use case as a starting point. And then the idea is that when you get those kinds of clusters of features, that those potentially could end up being the features that become your principal component vectors, or that become, say, for example, you have some cluster and you've got 10 variables in that cluster, and one of them you want to predict. And so you might use those other 9 features in that cluster in order to predict the 10th one. One thing that the life insurance company was curious about was they spend a lot of money on fluid-based metrics, so urinalysis and blood work, when they're trying to understand population health. And not only is it expensive for the company, but it's also invasive for the customer to have to pee in a cup and have their blood drawn just in order to get assigned some policy. And so their question was, is it possible to move towards a fluidless predictive model? And so, you know, that there's like another example of a use case. But yeah, the motivation behind the mutual information network was fundamentally just those mixed data types that the correlation networks, the hierarchical clustering explorer, the association networks were all based on only using kind of one type of data, whether it be continuous or binary, and the ability to integrate categoricals and ordinals along with continuous and binary variables was kind of the motivation there.
Okay. Thank you. Yeah, I was just wondering if a more creative application can also be applied. So, for example, can we use it also to find stories? For example, if like a data journalist want to find a story having like a bunch of data, I don't know, about Marvel characters or something like that, huge one. So you see this being also possible to apply for a more creative side of it? So
yeah, possibly. I mean, even in like my AI art, you know, those you could imagine that there might be a lot of metadata about the training data that I'm using, for example. Whether it's, you know, those HSV values, as I mentioned before, for k-means pixel clustering, but also subject matter, right? We have all of this, you know, GPT-3 generated image captioning tools and things like that. And so you could extract topics or words from the captions and, you know, use those as categorical features or, you know, one-hot encodings in order to get some high-dimensional data set where all of the observations are, say, images in a training data set, and then you have features that correspond to the metadata about the images or something. So yeah, I think it's a really ripe landscape for opportunity.
super cool. Thanks.
In the meantime, João, follow up on the question. So when there are several correlations levels and the filter was used to remove the not so strong correlated links, should we use a visual showing the most correlated items?
Yeah, so the idea with Sirius and with these networks is that as those edges are removed, the remaining edges you can hover over and then see the pairwise comparison of the two charts, and then you can look at the actual, for example, scatter plot if it's a correlation among two features.
Great. So maybe one last question to close, unless I don't think we have any more questions from our audience. But you study the emergent media, and you are also an artist. I was wondering if there is anything in particular that you are excited about, because emergent media is always changing, of course, and we seeing new ideas and new ways of showing not only media but also art in a way that's pretty much connected. Is there anything in particular that you are excited about for the future?
Yeah, so I'm really interested in the idea of like AI art being leveraged in new and unexpected ways. As I mentioned before, my you know, adjacency matrix of potted plants, or, you know, you'll see tools like Artbreeder that are being used as kind of source material for artistic inspiration. NVIDIA also has Canvas, which is based off of the original Gauguin, Gaugan, tool, which basically is like MS Paint, except that as you paint, it's actually kind of trying to create a photorealistic image from your blocky drawing. And so while I think that there is, as with any new technology, there's a lot of trepidation about, this technology replacing artists, I'm actually super excited about its potential in the art space. We had the same issue, by we, I mean, like, the artistic community with the advent of photography, right? Where because of photography, there was all of this, questioning, like, oh, what's the point of an artist if we have photorealistic images now? And it was in large part because of photography that we then got Impressionism. And we might not have had that otherwise, but it was sort of like, well, what do we do as artists that isn't photorealistic, that is novel, that still conveys the essence of our humanity beyond just the technical prowess. And so I really see artificial intelligence as a super exciting new tool in the artistic landscape. And yeah, I'm excited to see where it goes.
Great. Thank you very much. This was a very interesting talk, especially different from the ones that we have been doing lately. But like you said, data visualization is such a great field and an extensive field. So it's very nice to see all the applications, interesting projects that you have been doing. So thank you very much for joining us today.
Thank you for having me.
Thank you, Jane. Thanks for accepting again, and hope to see you in Lisbon at some point.
Soon.
So we say goodbye here, and we will go to our announcements. So bye-bye.
Bye-bye.
First, bye-bye.
I was very excited to tell you about our Pastel de Data. So as we mentioned briefly in the beginning, we have our new newsletter called Pastel de Data. This is actually going to be our second edition. So go to our website and subscribe if you are interested and to hear about it. We usually have an interview with the Portuguese. We are starting with Portuguese data practitioners, but we are of course expanding it. And we always have some interesting inspirations that we have, and also telling you what we have been doing. It's a monthly newsletter, so and the next one will be launched next week.
Okay, so now it's time for some more conferences. So just to let you know that EU DataVis is a free online international conference happening on the 23 and 24 of November, so already next week. And it's mainly focused on open data and data visualization, addressing the needs of the public sector across EU. So we really advise you to check and to enroll. It will be really nice. I personally, maybe that was my last conference that I attended before all this started, all this COVID thing, and it was really nice. So online it will be as good, I'm sure. So yeah, just and stay tuned. Thank you so much for joining, and keep coming to our channel, subscribe to our channel here, and follow us on social media, because we are always announcing new things. Hope to see you soon. Bye-bye. Thanks so much.
Bye. Thank you very much.